Imaging habitable zone exoplanets and getting these reflectance spectra that we've been talking about so far will require a dedicated space-based mission that hopefully we'll see fly in 20 years. Until then, we can still study exoplanet atmospheres, even those in the habitable zones, with the technique of transmission spectroscopy. This is the multi-wavelength study of exoplanets that transit directly in front of their stars from our point of view. And at all wavelengths, the planet will block out some light, and at some wavelengths, the exoplanet will appear larger, and the transit depth will be deeper because its atmosphere is absorbing or scattering light. For example, here's a transmission spectrum of Earth, as shown here on the left. If an alien astronomer were to look at Earth in front of the sun, it would block out about 85 parts per million of the sun's light. And at some wavelengths, there would be an additional 1 part per million blocked out by oxygen, water, carbon dioxide, or methane in our atmosphere. We'll call that additional decrease a delta D, and the D is the regular transit depth. So getting a successful detection of a 1 part per million feature is a really tall order, but we can do better if we go to smaller stars, because the scale of this effect scales inversely with the radius squared of the star. So for an M dwarf, an early M dwarf, we would get a 3 part per million delta D. And if we go to the latest M dwarfs, M9s, we can get a delta D as large as 160 parts per million for an Earth-like atmosphere, which is detectable even with current instrumentation. Very excitingly, we now have some exoplanets around small stars that surveys have found recently, dedicated surveys looking for these kinds of things that are going to be excellent targets for this. And we've heard about the TRAPPIST system, which has 7 roughly Earth-sized planets, 3 of which could be in the habitable zone. And just last week, LHS 1140b was announced. It's a super-Earth transiting a mid-M dwarf in its habitable zone. So in the best case scenario, we would measure the transit depth at multiple wavelengths, and any variations in the transit depth would be due to the planet's atmosphere. But this assumes that the transit chord is exactly the same as the unocculted photosphere. And this assumption is actually never correct. It just depends on the precision we're interested in, whether or not we just need to take this into account. In reality, stars are hot, noisy, chaotic places that make precise measurements very difficult, as anyone that does radio velocity measurements can tell you. And cool spots and hot faculae on the photosphere of the star that are not occulted by the exoplanet will not appear in our transit light curves, but they will affect the transit depths we measure. So even for relatively quiet stars, any difference between the transit chord and the mean unocculted photosphere will be imprinted on our measurements. For an illustration of the importance of this effect, we have to look no farther than our own solar system. And this is the 2012 transit of Venus, as recorded at 3 different wavelengths, from the extreme UV to the optical. And you can tell by eye in the UV that the transit chord is not the same as the rest of the photosphere. So if you're trying to measure the spectrum of Venus from these data, it would be very, very difficult with the sun's heterogeneity. The sun's actually a relatively quiet star. It only varies its total irradiance by about 0.1%, whereas all these M dwarf host stars of these exciting exoplanets all demonstrate rotational modulations on the order of 1%. So this is commonly interpreted as spots rotating in and out of our field of view. But additionally, hot faculae can affect this. And if there are axisymmetric features like latitudinal bands of spots, those won't contribute to photometric modulation, but they will impact the transmission spectrum. So we have examples today with our current precision of transmission spectra that are affected by this. There's the hot Jupiter HD 189. Its spectrum is shown here on the left. And even after accounting for the rotational modulation of unocculted spots, McCullough et al. Found that the remaining spectrum we see, this strong optical slope, can be explained by the presence of additional unocculted spots covering about 5% of the stellar disk. And in some work that I led on the sub-Neptune GJ 1214b, we found that its optical spectrum is sharply reduced, and that is the effect of unocculted faculae on its mid-M dwarf host star. So before we set out to detect biosignatures from Earth-like exoplanets, we need to ask ourselves, how might stellar heterogeneity affect these high precision measurements? So to that end, we're simulating the signals produced by host stars for a variety of situations. There are two proposed observational designs I want to talk about here. One is going to space with the James Webb Space Telescope and getting a low resolution spectrum from the 0.6 to 5.3 microns. We can look for absorption from O2, water, carbon dioxide. And another idea is using a ground-based giant telescope, like Giant Magellan Telescope, getting a very high resolution spectrum, and then actually we can detect the oxygen to A band in the exoplanet atmosphere, because the radial velocity of the planet and star will shift those lines away from the lines in our atmosphere, and we can peer between our lines and examine those. So we examined these two scenarios for a range of spectral types with a Earth-like exoplanet orbiting them, and then simulated the effect of 2% spots and 2% faculae. And these roughly produce the 1% photometric modulations that we see from these stars. So just stepping through the results in the near infrared, if we're looking at the effect of spots, I'm showing here the delta D produced as a function of wavelength. In gray is shown the transmission spectrum of Earth, just to guide your eye. The scale is arbitrary. For a K0 dwarf, the actual amplitude of these features is about 1 part per million. That's the blue shaded region you can barely see. And the effect produced by 2% spot coverage is about 25 parts per million. That's the blue line. If we go to cooler stars, we can get a larger biosignature because the star is smaller, but the effect of the star's heterogeneity is also larger. By the time we get to the M dwarfs, these stars are cool enough that there's differences in molecular opacity between the photosphere and the spots. And on the parts per million level, those differences are imparted onto the spectra that we see, and unfortunately overlap molecular features we're trying to get from the exoplanet. We go to mid-M dwarfs, the situation is the same, except now we're getting a much larger delta D produced by the planet. That's going to help us. And finally, at the very coolest M dwarfs, our delta D from the planet finally overcomes the delta D produced by the star, but still we're looking at a stellar signal that's a significant fraction of the planetary signal we're trying to measure. For the case of faculae, it's pretty much the same, but in reverse. Faculae will decrease your transit depth, so we have negative delta Ds here, and it's largely a relatively flat signal for the larger stars, and when you get to cool stars, faculae can impart molecular features on your spectra. So what if we look at high resolution optical measurements? So here I'm showing a much higher resolution spectrum. We're only looking at 0.01 microns instead of 5 microns. And in gray, this is the structure of the oxygen to A band at an arbitrary scale. Again, it's actually 1 part per million at this level. For the K0 dwarf, we get a signal from the star that's pretty flat across this narrow range, which is good, might be easy to take out, but it's about 80 times larger than the planetary signal. And the picture is the same. As you go to cooler dwarfs, you start getting more and more molecular features imparted onto your spectra. And unfortunately, the O2 A band is in the same spectral space as the strong potassium doublet. And for mid and late M dwarfs, there's differences in potassium opacity that can change your spectra on the order of 100 parts per million. And again, faculae have the opposite effect. And since I'm just using 2% faculae and 2% spots, faculae are hotter. They can put out more stellar light, so they end up making a larger impact, just assuming 2% coverage. And we can, for the mid and late M dwarfs, we can change our transit depths on the order of thousands of parts per million. So to summarize, we looked at K0 to M9, and we simulated the effect of spots. And this kind of spot coverage, if you integrate it over the I band, would produce a rotational variation on the order of 0.5 to 1%. And the signals we'd be looking from the planet are about 1 to 160 parts per million. In the near infrared, the stellar signal that corresponds to these variabilities is much larger than the planetary signal for all but the latest M dwarfs. And in the optical, the stellar signal is always larger. Picture is the same for faculae, but with opposite signs, and the effect's a little bit larger because I'm just, again, assuming 2% coverage, not scaling for the actual photometry. So the main point you should take away from this is that stellar photospheric heterogeneities affect all transmission spectra, and it's a matter of scale. And when we try to get these really high precision measurements from exoplanets, it's going to affect all transmission spectra that we try to get. Variability on the 1% level will pit spectral features in your near-infrared spectra on the 10 to 100 ppm level. And unfortunately, the potassium doublet and the coincidence of the oxygen to A band is going to really complicate optical high-resolution observations. So as we're planning to take these steps and to get high precision measurements of exoplanet atmospheres, we should also try to understand stellar photospheres to that same level of precision. And thank you for your attention.
We have time for a couple questions, and I want to start with one, which is, did you look at the 0.69 micron oxygen band or the 1.27 micron oxygen band, which may not have the problems with the potassium doublet overlap?
I only looked at the 0.69 for this because that was the idea was you could get it from the ground with a high resolution measurement. I haven't looked at the near infrared oxygen band as well. Yeah.
Thanks. Is this on? Okay. Thanks for the great talk. It seems, though, that observing the parent star and having a good understanding of spectral features for stellar atmospheres can just help you remove or account for these effects. You have variability, of course, which is the key factor, but otherwise, they're stable. If they're stable, you can just account for them in your modeling, and you'll still see the transit feature in the same way. Is that correct? Can you explain how exactly it would affect, in different circumstances, your final results?
Yeah, so the complicated thing is with photometry, what we have to assume is that the brightest photometry we see corresponds to an immaculate photosphere with no features. And that's kind of, in the case of 189, the hot Jupiter spectrum that I showed, that was the assumption that the authors took. So we have immaculate photosphere, and then at the different points that we measured our actual data, we can take the brightness of the star at that point and correct for the effect. And they did that. They thought that the stellar photosphere had about 2% coverage, but McCullough et al. Showed that in reality there's a latitudinal band of unocculted spots that don't contribute to photometric modulations because they are axisymmetric, and they are affecting the resulting spectrum. So one way we can attack this is we can get much longer photometric monitoring campaigns, and we can increase our chances that we're actually going to see the star when it has this immaculate photosphere and we have our 0 point. But other than that, if we don't know what the 0 point is, it's not going to be possible. Maybe Doppler imaging of stars can help us get to that.
Thank you. One really quick question, please.
Just quickly, nice simulations. I think it would be important to include magnetic fields because they will affect the depth of the molecular bands which you calculated. That would be, for M dwarfs, very important. Yeah?
Yeah, I'd love to talk to you about that. I'm just taking a very simple approach, and I'd like to learn more.
Yes, let's talk about it. Okay.